3. Video number 3. Stress. This case, with Hooke's law, we have an issue that if we changed the length of the spring, the constant would change. So that's not very good. If you're an engineer, okay, and you want to go and read your book of constants, so you've got your little book, and it has a whole lot of constants in it, okay, all these constants. However, and you wanted to use a piece of material to build a bridge, you would want to know the strength of it, okay? And you can't use Hooke's law, the spring constant, K, because it changes depending on the length of the material and so on. So what they're going to use something called the Young's modulus. And the Young's modulus is going to be related to stress and strain, okay? In this case, we're going to use the tensile force, which is the same thing that we've seen before, which we used for the spring constant, but we're going to divide it by the area of the thing we're stretching. Okay, so it's force per unit area applied to a sample of material. Okay, so here's our material, and we're going to grab a force and pull on it, and depending on the size of the area and force, you're going to get the stress. What's the symbol of stress? Well, sigma, okay, another Greek letter. And how do you find the formula? Well, we just said it's just force divided by area. Okay, what's the derived unit? You can work that out. However, if you look at this, what's force divided by area? That happens to be the defining formula of pressure. So it must be pascals. Very handy. Strain is a different one. Okay, strain is how much you extend per unit length. So if you had something that extends 10 centimeters and the whole length was 1 meter, well, it's going to be 0.1 meters per meter will be your strain. Okay, if you have 5 meters of it, well, you can easily know what your extension will be if you know what the strain is. It's always going to be 0.1 meters for every meter. So if you had 5 meters, it will be 0.5 meters. Okay, and that always comes back to the same. If you do 0.5 divided by 5, it comes back to the original 0.1 over 1. So the change in length per unit length of a sample of material. So this one here has the symbol epsilon, okay? So you could just go like this, little curly E, okay? What's the formula? Okay, well, it's just going to be your X divided by L, where X is your change in length, L is your unit, is your length, okay, that you're measuring. Derived unit, well, it's going to be meters divided by meters, so there is no unit. And same with this one. Essentially, it's a ratio, okay? It's, or you could say it's percentage or fraction. It's how much it is extended fractionally per original length. Young's modulus, okay? Essentially, you could define it by the formula, okay? Don't just write it like that. You need to write out Young's modulus can be defined by the word equation, stress over strain. Oh, Young's modulus equals stress over strain. So write it out in full. But the definition is essentially the formula. Okay, what's the symbol? Okay, capital E. Now what's, need to work out what that is. But capital E is your symbol for that. And the formula is going to be stress over strain, okay, in this case. What's the derived unit? Okay, well, it's pascals divided by something else, so you can work that one out. But essentially it's the same as stress, because we're dividing it by no unit. What's the SI unit? Well, it's pascals divided by no unit.